To understand the practicalities that underpin the theory regarding time travel, the ideas presented by Einstein's theory of special relativity must be addressed. These ideas must also be related to the phenomenon of time dilation. The Lorentz factor is a conversion factor which is key when used with regards to special relativity and the idea of variable time. It is the factor by which time, length and relative mass of an object are variable in regards to motion, allowing unusual distortion to occur regarding alternate fields of view. This equation gives the Lorentz factor in terms of speed of light, c, which is a constant, as well as velocity between inertial frames of reference. Inertial frames of reference can be defined as frames in which Newton's laws are observed, particularly his first law, law of inertia. This law refers to the tendency of objects to resist changes in their state of motion. Simply, objects at rest will stay at rest whilst objects in motion will stay in motion at the same velocity, speed and direction, so long as there are no resultant forces acting upon it. That is to say, the object's state of motion will only change if it is acted upon by an unbalanced force. This principle is clearly apparent in modern cars as it has influenced the design of seat belts. If we take a car to be in motion with a constant velocity, v1, in a closed system, uninfluenced by resistive forces such as air resistance, it and its passenger will be obeying the laws of inertia by traveling forwards at a constant rate. However, if the car were to brake strongly, you would notice that, as a passenger, you naturally slide forwards on your seat. This is occurring because the forces acting on the car are now unbalanced. Hence its velocity has changed, but the passenger has experienced no opposing forces, so will resist this change in motion and continue to travel at the same velocity, hence obeying Newton's laws and therefore sliding on the seat. As such, a seat belt is necessary in order to oppose v4 and prevent the passenger traveling until impact with the windscreen. This relates back to the idea of inertial frames of reference, as it tells us that Earth can be viewed as inertial given that an object at rest will not move from its rest position unless external forces act upon it. In reality, the rotation of the Earth gives objects that seem to be experiencing no external forces a slight acceleration, hence it is non-inertial. However, it is important to note that both inertial and non-inertial frames can greatly affect perception of an event, and whilst motion does not necessarily create a non-inertial reference frame, some motion may. So how does this apply to time travel? To understand this, the ideas presented by Albert Einstein and his works regarding special relativity must be addressed. He claims that the laws of physics are observed equally by all systems, regardless of velocity, as well as that the speed of light, c, is a constant across all systems. It is these principles upon which time dilation, and therefore time travel, are grounded. Time dilation, t-, is the idea that time moves at different rates regarding independent frames of reference. It is given by this equation, where t is dilated time, t is standard time, v is velocity and c is the speed of light. Through the use of this equation, you are able to determine that time appears move more slowly the greater the velocity. This is best shown through example. Take a theoretical situation of two parallel ships in space, A and B. Shuttle A contains a light source, a detector and a plane mirror. Shuttle B is empty, other than for the pilot, observer B. The time taken for the light to travel from the source to the mirror and back to the detector is observed by the pilot of each ship. The only difference being is that the observer of Shuttle A is moving at a constant velocity, whilst Shuttle B is stationary. Note that this makes both frames of reference inertial. Hence the Lorentz constant may be applied. Observer A Notice how by moving at the same velocity of the shuttle, observer A experiences, as such, no motion. As a result, light travels perpendicularly to the mirror and then returns along the same path. Observer B. As you can see, the observation of light's travel as observed by a stationary field of view differs greatly to that of observer A, given that the motion of the system is very apparent. For observer B, the whole system had traveled distance, d, at velocity v. Hence it appears that in this reference frame light has traveled a further distance. This poses the question as to why two different values for time are recorded, and which is correct. Almost counterintuitively, both values are correct, which resulted in the creation of the time dilation equation. Hence, for this theory to stand, given that c is constant, time itself must be distorted in some way to make the maths work out. Time in fact can stretch such that the faster that you move, the slower it appears to flow to others observing your reference frame. As such, hop in, hop out, time travel is not possible. However, time travel into the future is a definite possibility.